Welcome to our lesson on circle theorems. We are going to continue a little bit to look at theorems number 6 and 7 in this particular lesson. Theorem number 6 and 7, which are based on the cyclic quadrilateral. Now, before we do that, we're going to look at an example on the three theorems that are based on the angles in a circle, which we have looked at in a previous lesson. Of course, there was a slight error in our presentation. On theorem number 3, we should have written this as angle at the center is twice angle at the circumference. We're explaining this correctly, but what we wrote is a little bit different. So this is supposed to be angle at the center is twice angle at the circumference. So we're explaining this theorem in the previous lesson, where we said this angle at the center will be 2 times the size of the angle at the circumference. This is one of the theorems that we looked at in the previous lesson. So before we look at the 2 theorems, theorem number 6 and theorem number 7, which are based on the cyclic quadrilateral, we are going to look at an example or 2 on what we have covered so far. So there is a question here which says, in the diagram, PR is the diameter of a circle with center O, and then Q and S are points on the circumference, and there's a tangent. So we'll look at the theorem when we to do the tangent later on. But with that information, the question is to calculate the angle at R from P and S, and the angle at R from P and Q. In short, we are calculating for angle PRS, PRS, and PRQ. PRS and PRQ. Now, if we sketch this this question here, we have these 4 points. We have these 4 points P, Q, R, and S, which are on the circumference. P, Q, R, and S, they are on the circumference of the circle. Then we have 2 angles that are coming from QR. So we have a chord here, which is also going to S. Okay, that is coming from P. All right. The information that we have in the question is that there is a 42 degrees at P and 26 degrees at Q with the center O. So the center O is here. Okay. So we have an angle here, and we have an angle there. 42 and 26. 42 and 26. This is 42 degrees, and this is 26 degrees. So we want to find the angle PRS and PRQ. PRS and PRQ. PRQ. We will not look at the last part of the question. The last part of the question says find PTQ. So because PTQ involves the tangent, we will not look at it now because we have not yet covered that theorem. So from what we have covered so far, PRS is this angle here. Okay, PRS is this angle here. PRS is the angle at R, subtended on the chord PS or the arc PS. So from the theorems we have covered, there is a theorem number 4, which, for example, says angles that are in the same segment, they are equal. So you can see that the angle PRS, this one here, this angle is coming from the same points as the angle at Q, this one here. Okay, so these two angles are coming from the same chord PS, which means PRS is equal to is equal to PQS. PRS is equal to PQS, which is 26 degrees, because these are in the same segment. These are angles in the same segment. Angles in the same segment, according to theorem number 4. Angles in the same segment, they are equal. So it means the angle PRS is 26 degrees. If we look at PRQ is this angle here. That is PRQ. All right. So now PRQ, of course, there is also an angle which is related to PRQ. It's that angle there, which is PSQ. That angle is also coming from the same segment PQ. So if we had known the angle PSQ, we are going to say PRQ is equal to PSQ. All right. But since we don't have the angle PSQ, we have to look elsewhere for that information. Now, we can see that the center of the circle is given. Okay, and so it means we have a semicircle. We have a semicircle situation in the question. Let me just redraft here. So if we look at PR, we are told that PR as a chord is actually the diameter because it has a center there. So if there is an angle subtended from this chord, it means it's a 90 degrees. So if we look at this angle PQR, it means this is what? It's a right angle according to theorem number 5. An angle in a semicircle is what? It's a right angle. So this PQR has been divided. The angle has been divided. Of course, we have this one. This is 42 degrees. But this 90 has been divided into one part, which is 26. Okay? So, but we know that the whole angle is what? It's 90 degrees. So because the whole angle is 90 degrees, it means we can do what? We can add the 90 and the 42. Okay, we can add 90 plus 42 to get 132. So because this PQR is a triangle, it means we'll get 132 from 180 to find the angle. 48 degrees. So in short, PRQ is 48 degrees. So we have used the theorem. We have used the theorem number 4 and theorem number 5. Theorem number 4 says angles in the same segment, they are equal. So we have used that theorem to get our PRS. Then we have used the theorem which says angles in semicircle are 90 degrees or right angles. We have used that theorem number 5 to help us interpret and get around to find the angle PRQ. So that is how we solve angles involving the first 5 theorems that we have covered. So let's look at theorem number 6 and theorem number 7, which are based on the cyclic quadrilateral. The cyclic quadrilateral. So we first need to understand what exactly do we mean by cyclic quadrilateral. So a cyclic quadrilateral, first of all, we know what a quadrilateral is. A quadrilateral is any four-sided polygon. A plane figure that has 4 sides will be called a quadrilateral. So what exactly is a cyclic quadrilateral? So a cyclic quadrilateral, it means it's a quadrilateral that has all its 4 vertices on the circumference. Okay, let's say we have A there, B there, C there, and D here. If all the four corners or 4 vertices of this quadrilateral, if all the 4 vertices are on the circumference, if all the 4 vertices of this quadrilateral, if they are on the circumference of the circle, then we'll call that a cyclic quadrilateral. So the next 2 theorems, which is theorem number 6 and theorem number 7, these are based on the cyclic quadrilateral. So theorem number 6 states that opposite angles of a cyclic quadrilateral add up to 180. Opposite angles of a cyclic quadrilateral. Let me just abbreviate this as CQ, cyclic quadrilateral. They add up to 180. Okay, so that is theorem number 6. What that means is that if you have this angle here at A, if this angle at A is given, you can find the angle at C, because these opposite angles, they add up to 180 degrees. Okay, of course, the explanation of this theorem is coming from the theorems that we have looked at, which are that the angle at the center is twice the angle at the circumference. The angle at the circumference is half. Yeah, okay. The angle at the circumference is half of the angle at the center. So if, for example, we put an angle here at the center, if this is the center, and we put an angle on AB, we would say the angle at the center is 2 times, okay? This will be, if the angle at A is x, then the angle at the center is 2x, okay? So if we do the same okay, if we do the same the other side, the angle at C will also be half of an angle that we can make where at the center here. So what will happen is that the analysis will give us, because the angles at the center will add up to 360, okay, a complete 10. It means the angles at the circumference there, they will add up to 180. They will be half of what is happening at the center in whichever direction you look at them. So theorem number 6 states that opposite angles of a cyclic quadrilateral will add up to 180. And then theorem number 7, also based on the cyclic quadrilateral, states that if we extend and create an external angle, okay, if you extend one side of this cyclic quadrilateral, if you extend one side of the cyclic quadrilateral to create an exterior angle, which means an angle which is outside that cyclic quadrilateral, that exterior angle will be equal to the angle which is inside but opposite exterior angle of a cyclic quadrilateral, exterior angle of a cyclic quadrilateral, CQ, cyclic quadrilateral, is equal to the angle which is inside but opposite, is equal to the interior opposite angle, equal to interior opposite. Interior opposite angle. Okay, so if we go to our demonstration here, what we are saying is that, for example, by creating this exterior angle, okay, this angle is outside the cyclic quadrilateral. We have created it by extending one side of the cyclic quadrilateral. So we have created an exterior angle. Now, this angle is adjacent to an angle which is inside here, isn't it? Okay, it's adjacent, it's next to. But because it's next to, it means when we add this angle plus this angle, we get a straight line, we get 180. All right, so because the addition of this angle and the addition of this exterior angle and this adjacent interior angle, the addition gives us 180. All right, and you remember we have also said the opposite angles here in the inside of the cyclic quadrilateral, the angle at C and the angle at A, they also add up to 180. All right, which means this angle at A, when added to the angle at C, you get 180. And the exterior angle also, this exterior angle of the cyclic quadrilateral, when added to C, you also get 180. It therefore means that this exterior angle here is equal to the one which is opposite, okay? Not the adjacent, no, not the next one inside, but the interior opposite angle. So you have an exterior angle to the cyclic quadrilateral, which has an adjacent interior angle, but now the one which is opposite that adjacent angle, that opposite angle which is inside the cyclic quadrilateral, it means it's the same, okay? They are equal. So the exterior angle is always equal to the interior opposite angle, because just like the adjacent interior, they add up to 180. We'll look at an example in our next lesson.